Before we can troubleshoot a system, first thing, of course, is we need to know exactly how it's supposed to work, right? So if you don't know what it's supposed to do when it's working, then there's no way in the world you're going to know what's wrong to fix it when it don't work. So most of your manufacturing lines, or your automated manufacturing lines, all go in a sequence. And the trick is to learn the sequence, and then, of course, what's required at each step of the sequence. So if we can take the sequence and break it down to individual steps, and then see what's required to cause it to go to the next step, then we'll know exactly where to go and look for our problems. So this is the pick and place. So this is basically the layout that we've already looked at of what we call the distribution station, or what also called module 1. This is the one all the way on the left hand side. And it's got a magazine, and we fill this full up with our cells for our directional control valves. And then we've looked at how these sensors are labeled. We know if it's got a B, it's a sensor, right? And we also look to know that this means this is in the circuit that controls the first pneumatic actuator, right? We looked at that last class. We know it's B1, and then this would be its location from the top down. So this is kind of different than normally when we number things, we number it from the power source out, but on these we number it from the actuator down. So the actuator would be the first one, then it would come down back toward the power source for these numbers. But these are two Hall effect sensors right here. That indicates when the cylinder is either fully extended or fully retracted. These are valves, so these are flow control valves. So these guys right here actually control the flow of how fast the actuator moves. This one on the back side, this would control how fast it extends. And then this guy right here would control how fast it will retract. Unfortunately, it's got knobs on it. And of course, what will people do if something's not doing quite right? They go out and do what? Start turning knobs. So if if it's retracting real slow or extending too fast and jumps around, then odds are something's going wrong with your flow control valves. Then we got a magazine, and B1, this guy right here it's actually working with this, and it's detecting, it's a diffuse sensor. It's a photoelectric diffuse sensor, and it's what's actually detecting if there's a block in the magazine. And then of course, so what happens if this guy's retracted and we hit start? Then this guy here would extend. How does it know it's extended? So it would put pressure on this side. It would exhaust that side. 1B2 would go true, and it knows it's extended. And then your programmable controller, once this is extended, it knows it's ready to go to the first step. So if nothing happened when I press the button, what would you think would be the sequence? What is it looking for, number one? What would you think it was looking for, the first thing before it extended itself? What did you say, Jimmy? If there was a block in there, right? So if we looked at the sequence, that if it didn't extend, then I would know right off the bat to extend. This B1's got to be true, right? You understand? If B1's true and then it don't extend, what would probably be the next problem? What would have to be true before it extends? Well, it would have to know it's fully retracted, right? So it would look at what? It would look at 1B1. And if it's a part present and 1B1's true, then the PLC says, okay, go ahead and do what? Extend. So it would come out. And then how does it know when it's fully extended before it can go to the next step? Well, it's going to sit here and look at what? 1B2. So now 1B2. So 1B1, B1, 1B1, 1B2. And now we're ready to go to the next step. Well, what we're looking at here is this guy right here is not looking, it's not looking at 1B1, it's not looking at B1, it's looking for what? 1B2, because that's all it cares about, because it's waiting on this thing to be extended. So as soon as 1B2 goes true, then this is going to tell this guy to do what? Now what's it looking for? Well, it's looking for this guy to be what? Fully retracted. 1B1, 1B2 is full. It's fully retracted. This is full. So what's this going to do now? It's going to extend. How does it know it's retracted? Excuse me. Well, it's got a sensor on it's fully retracted right here where it says 3B1. So before it extends, it's going to look for what? It's going to look to see if 1B2 on the previous slide was what? Was true. It's going to look to see what? If 1B1 was true. And if this guy right here, which we don't see, we'll have to look it up to see if it's fully retracted. And if all that's true, then your PLC would do what? Would know to do what? To extend it. So what we're saying, if I know these sensors and I get up here and my thing goes out fully, and then this guy here don't drop down, then I know it's either going to be what? It's either going to be the 1B2 on the other one, or it's going to be one of these guys over here we just talked about. If all that's true, it knows it can do what? It knows it's going to extend here. Well, how does it know it's fully extended? How does it know when to turn the vacuum on? Well, when this sensor right here, this 3B2, when it goes through, because now it knows it's what? Fully extended, it turns the vacuum on. Well, how does it know the vacuum's on? Well, there's a pressure switch down there that says, okay, the vacuum's on. When it knows the vacuum's on, it knows it can do what? It can retract it. And it knows it's holding something. Because what happens if the block is turned wrong or it hits on the side or somehow we don't get a block over there, it's not going to generate that vacuum. So the pressure switch would never go true. So, and what we're looking at, okay, if I know the sequence and it stops here, it gets this far, instead of me going back to where it's supposed to, I'm only concerned with what's required to cause it to go to the next step, right? You understand that? And so this is what they're going to do. So this is the actual line here, which we've seen in life. This is the picture. So this is pick and place. Pick and place is a common use for robots and different types of things. Pick and place just means you're going to move something around. Okay. So we have one of the main functions of robots is pick and place. It's just doing what? Moving it from here over to there. Okay. So I think this actually gets feed cylinder, pickup cylinder, linear transfer cylinder, or what I call the gantry. Vacuum suction, vacuum generator, valve body pickup position, release position, and then down, right? So this is the sequence. So right now, this guy right here is true, and this guy right here is true. So what does it know? It knows the block's present, and it's ready to do what? It's ready to extend the cylinder. Pick up. I think it's animated. Vacuum off. Feed cylinder retracted, on, it knows to do what? Understand that? Are we okay? Okay. Okay, now we're fully extended. This guy says I'm extended, right? Then what's going to happen? It's looking for this guy to be on and this guy to be on, which means it's what? It's fully retracted. This one you can't see. Okay, feed cylinder extended. Got the indicator to our PLC, valve body must be in place, so it's going to drop down. So what's got to occur now before it moves on? It already knows these was true because they wasn't true. Well, we got two things now. This guy's got to go true, indicating I'm fully extended. And then what else has got to happen? Once it's fully extended, it's going to do what? It's going to turn on the vacuum. And then it's going to check to see if it generated a vacuum. If that suction cup is open, it's not going to generate a vacuum. Somebody's going to say something, I'm listening. Right, or we've had every once in a while these little suction cups, and we had to adjust this. So for a while, it wasn't adjusted quite right. So what was happening, I think if you look, you'll see two little plastic things in there. So what was happening is the suction cup would drop down, and the suction cup actually extended too far, and then it would roll around. So the suction cup would actually flip up. And so if you look, and it would do it every once in a while, but if you go over and look real close, on this brace right here, we've got it's got a thin little plastic wire tie stuck on both sides. So we had to extend that, good gracious, less than a millimeter. So maybe a tenth of a millimeter. Just to make that suction cup come down and hit flat and not do what? Not flip up. So little things like that, you find that, if you look at the Festo line, you'll see a spring over there. And all it's doing is we found out that every time it would come down here in the valve body, or the cylinder wouldn't slide all the way into the thing. And when it moved, it would jam it up. So all that thing is doing when it comes by is just pushing it into the slot real good, so it'll go around and work. And these are the little things that you learn while things are happening, right? So I've never seen a manufacturing line come ready to run, even though they might run it in their plant, then they get it out here, and it's still got little quirks they got to do. We had to came over here when they first put the Amatro line in. They put it on this side of the room, and the Festo line was over in the other class. Well, we just figured out how we was going to arrange those, and we moved the Amatro line from this side of the room to that side of the room, and the robot was missing everything about that much, just because of the layout of the room. So there's no way in the world this concrete floor is going to be perfect, right? You understand that? And so over there, it's kind of a little bit different, and the robot missed its points. So what did we have to do when we moved it over there? We had to come back and reteach all the points on that robot. So what we're saying, if I came up and I had a chart that showed me the sequence, if I learned this sequence and develop a chart on what's required to cause this, and then all of a sudden it stops right there and nothing happens, but it extended, then I know it's probably not, it might not be generating a vacuum, and I would go there. I wouldn't go back to my hopper. I wouldn't do that, right? I'd go to where my problem occurs. So this is the first thing we're going to do. We're going to develop these charts that we're going to use. Vacuum on, then it's going to drop it down on the cradle. But all it's doing is just saying, okay, I'm not checking what was required to go to the previous step, because that was okay. All I'm checking is what's required to go what? To the next step, yeah. So we come up here and we have these charts. Let's see if we can get to it, because this is a pretty good little animation. And then it's ready to go and ready to start over again, right? Steps, so we come up here, of course we know inputs, outputs. This is the programmable controller, and that's all it's looking for. So we got charts, so these are the steps: extend cylinder, extend feed cylinder, extend pickup cylinder, switch on the vacuum to pick up a part, retract feed cylinder. So these are the major steps, right? But what's nice about when y'all learn this, what's nice about the Amatro line is we can single step that line for every step. And then we can document what's required to cause it to go to the next step. The Festo, we can't do that. Festo says it's got a single, but it's a single loop. So if you put the Festo on manual, it'll run a whole cycle and stop at the start of the cycle. But the Amatro line will actually stop. Its manual is a single step. So you can actually see each step of what the thing goes through. And of course, if you could take this and lay it in some type of flow chart like this, what's required? So push button, press the start button, PLC logic, feed cylinder extends, but what we're trying to do is figure out what it does what's required. Feed cylinder extended sensor triggered, and once that triggered, it does what? It moves on, right? You understand? You'll follow me so far. So this is what Siemens calls a function chart. And by the way, there's a language we can program a PLC using this. So in PLCs, we teach a programming language called ladder, which is the predominant language used over here. Over in Germany, they program a PLC like this. So they just put this chart, that you can literally put this chart into a program. Now when you look at the program, you're in a sequence, right? So here it says, okay, by the way, this means and. So if FB1 and B1 is true and the start button is pressed, and B2B1 is true, and 3B1 is true, and 1B1 is true, then go to this step. And what's it going to cause to happen? It's going to cause the Q5 or output 5, module 4, which is one of the modules on one of the. So anybody here had PLC? The Siemens PLC, Allen Bradley PLCs goes in words, groups of 16 bits. The Siemens PLCs goes in bytes, which would be groups of 7 bits. So what that means is if I was going to start in the Allen Bradley PLC and I had a 16-bit module, then my addresses would go from 1:0/0 all the way up to 1:0/50. That would be the way we'd address that. So we would have the whole word. If I had a 16-bit input module on a Siemens PLC, then the way we address on that, we start off with I, but we don't put a colon. We'll come up here and put the slot number, and then we put a period, and then we put a bit. So this is the way you address the Siemens PLCs. So these right here are equivalent instructions. Well, I would go from word, so this would be byte 0, and this would go up to input 0.7, and then on the same module, it would go from input 1.0 to input 1.7. So Siemens so a 16-bit module would go through 2 bytes on a Siemens PLC. So that's why we get up into these high numbers, because this guy here, I think it's got 24 inputs. 24 inputs, right? I think 24. We have to go back and look. So that means we would go through these different byte numbers. So these are outputs. So in Allen Bradley, to address, we use an O to say I'm going to generate, the program's going to generate an output. But if you ever program a PLC, an Allen Bradley PLC, I'm going to use an RS Logic 500, somewhere down the line, you're going to use a 0 for an O, or you're going to use an O for a 0. Somewhere, I guarantee, it's guaranteed. And then, of course, your line, when you check your line to see if it'll compile over, it's going to give you an error, and you're out there trying to figure out what's wrong, and the O and the 0 look almost alike, and it's hard to find. So what Siemens decided to do, instead of using O to designate an output, they call their outputs Q. So that's 2 big differences in the Siemens PLCs and the Allen Bradley PLCs is the way they address their boards. So this says byte 4, output number 5 would go true, which is what's going to cause to happen. It's going to cause this cylinder to extend. When it gets extended, it's going to do what? It's going to cause 1B2 to go through. What's required to go to the next step? 1B2 has to be true. So if 1B2 is true, then it'll go to the next step. Y'all understand that? It goes to step 2. What's step 2 going to do? Well, step 2 is going to cause output 4.6 to go true. This is going to extend the pickup cylinder. When it's extended, this is going to affect 3B2. Okay, so what's required to go to the next step? 3B2 has to be true. So if it's true, it goes to this step right here. This is going to cause Q5 output, byte 5, output 3 to go true. Is going to turn on the vacuum pump. This is going to affect that pressure switch that we was talking about. So right now, if I get down here, and then my Q5, my cylinder does not retract, then I'm not going to worry about this. I'm not going to worry about that. I'm not going to worry about that. I'm going to check that guy right there. Because it got into step 2, It got into step 3, but it didn't go to step 4. So right off the bat, I know where to go first. I don't have to figure out. I'm not going to go all the way to the front. I'm going to go to the step it don't go to, and then I'm going to look right here. All I got to do now is look right here and see what is required to make it go to that step. So if it got down here, I'm not worried about those up there, right? You understand? And this is called a function chart. So if I had this function chart for the whole operation of the line, and it stops at step number 10, then I'm not worried about step 9. I'm seeing what's required to cause it to go to what? Step 10. And I'd go right there and I would figure out my problem. The most likely, I'm not saying that is the problem, but that's probably a 90% chance that you've isolated that problem that fast. So you have people that would go all the way back to the front. We've had it in this class. They'd go all the way back to the front. And why? Because why go all the way back to the front? Go to the step is what it stops on and see what's required to go to that step and go to that part and get that and fix that out, right? And see if that's the problem. And this is called function charts, guys. These are great. So you're going to make a function chart. One of your labs, the first lab you're going to do. Well, the first lab we'll do when we split up is we'll take the line apart, we'll split it apart so y'all can figure out how to put it back together. So what we're going to have to make sure we do is when the first group at the end of the class, they're always going to have to do what? Put it back together and make sure it's still working. So how to route the tubing, how to route the arrow hoses, how to hook it up on the external stuff that we got when we split it apart. So when we split it apart, that's what that big manifold running down the back of the wall is. So we can move one module way out over here and hook it up to its own power and hook it up to its own power source. So you'll do function charts. Then you'll present your function chart to the other 4 people in the class. And then we'll move to the next person. And then once you try this, when you actually do your troubleshooting, we'll let you use the function chart that was set up by Siemens. But we just want you to get the feel of trying to make these things yourself. Because look at this, if you have one of these available, so if you go into a place and they don't have this, and something breaks down, just watch the confusion. Right? Until the guy that comes out there that's worked for 20 years and knows the sequence. But with this, you don't have to have that guy there, right? Or that person. They don't have to be there because now you can say, okay, what didn't happen? Well, the feed cylinder didn't extend. Okay, what would that be? Oh, I'll go out here and check out 2P1, right? And you don't have to find, Joe Blow or Angel out there to come out and do what? And fix this thing for you. So these are the guys. These are the people you worship, and they get the line going. But they have the sequence chart in their head. But we don't want that. We want any technician to be able to do what. So that's what you could do. Once you learn how to develop these, you could literally just go out there and watch this thing, or talk to this person. What do I need here? What goes there? And set this up. And then next time you just come back and hit this, and you'll go to the problem right off the bat. Step, transition. This is the rest of it. So I got down to step 9. It died on step 9. Didn't get to step 9. Did step 8. Didn't get to step 9. Where would you go to? Yeah. So see how fast that would be if you had that information. And this is why Siemens. This is the way they learn to program their PLCs in this language right here. It's called a function chart diagram. And it's really cool. So you put a step, then you put what's required. They call it transition. What's required to transition to the next step. So they make these charts when they program their PLCs. Unfortunately, over here in the United States, the predominant language is ladder, and we are a stubborn breed over here. Even wearing these, right? So we're stubborn. Originally, they tried to convert us over to the metric system. Y'all probably don't remember that. So you might get into an older car, it's not real old, and they would have both kilometers per hour and miles per hour on there. And they came up on all these mileage sticks out there. They had 2. They had one for kilometers and one for miles. And all the signs up there that showed you the distance had miles and kilometers. Their ultimate goal was to eventually get rid of the miles and once we got used to it, and get us to go over to the metric system. And who won that battle? Yeah, we won that battle. We said, we ain't gonna learn nothing new, we know this. So we're stubborn breed. What does the actual error situation look like? What step did it stop on? What was required to cause it to that step? So one of the first labs we'll do is we'll come in and we'll get these whiteboards out. Every group will have their own whiteboard. And what you'll do is you'll sit there and you'll put it on single step, you'll step it through, you'll identify the sensors. So I'll give you all the diagram of where all the sensors are at. The amateur line doesn't label much, but we do have pictures that show you where they're at. And figure out what's required to transition from step to step and see how good you do on your chart. And then after that, like I said, once we actually go to lab, then we'll let y'all use the documents that, so Amatro did not do this. This was done by Siemens. So when Siemens got these lines, these Amatro lines, they did these charts for us. So we got the whole manual that comes from there. The other chart, of course, is that a video? We've got these videos, so. So we'll have these, by the way, this is decision. So this guy says, I've got two ways I can go. If B2 equals 0, then I'll do this. I need to be. I really took to this because this was a lot like flow charting in computers. Used to when you wrote the program, but you didn't enter the program in the computer. So we had all these programmers, and they'd write these programs, and then they'd give them to a key punch operator, and they would punch holes in these cards that represented your code. And then they would come in and they would try to download it into the computer. If it didn't work, if you got errors, then they would come back and give you those errors, and you'd come back and try to fix them. So the ultimate goal before you even wrote your program is to see if the program actually flowed. So we had all these things we call flow charts. So usually what you would do when you started a program is first of all you'd make this flow chart with all these symbols and stuff. And if it didn't flow in the flow chart, it wouldn't flow in the program, right? So once you got all your bugs or figured out the program would flow okay, then you wrote the program. What we do now, since everything is so fast, is we just start hit and miss, and we'll throw some code in there. If it don't work, we'll go back and fix it. And you do your own programming now. So even in PLCs, we go ahead and put the program in there, then we do what? Then we see if it works. If it don't work, then we try to do what? Figure it out. So this is saying when I get down to this spot right here, it's going to make a decision depending on what? Depending on B2. If B2 is a 0, then it's going to go this route right here. If B2 is a 1, then it's going to go this route right here. And this is actually, this B2 is actually the metal detector on the conveyor belt. So if it's metal, it's going to push it over to the inside, into the inside of the conveyor belt. If it's plastic, it's going to let it come through. But it all depends on that metal detector. So this would be another way we can represent this. So this is the way, and of course this falls through here, and then it comes back together. No matter which direction it comes back together, and then it goes through 6. So this is the way we do decisions in this. In flow charts, we use a triangle. And we'd come in like this, and one way would go that way, and one way would go that way. And down here, this might be a yes, and over here, this one might be a no. So that was the symbol we used in flow charting. But here, all the symbols are the same. So this is the way we can show you that the things makes decisions, right? So if if it kept feeding the metal ones, down the same side that the plastic goes down, then your problem would be what? It'd be 2B2. 2B2 is always putting out a 0, which indicates it's plastic. Oh, they're doing the same thing I did. So these are called function blocks. In PLCs, they call it function chart diagram, FCD. And if you had this chart right here, and you knew how the transitions and stuff, you could write this PLC program. And what's nice about that, like I said, when you print that off, you have these things for the technician. If you got a ladder diagram, then the technician's got to figure out the logic of the ladder diagram. Well, this guy right here actually shows you what? Shows you the sequence. The other diagram that they like over there is this guy right here. And of course, this is displacement step. So once you do your function chart, you'll also do a displacement step. I want to do that. This is the same section. So they're doing exactly the same thing. I'm not going to go through. So this is displacement. So what we do on a displacement step is we say out here, we're saying when does the cylinder extend? So this is a feed cylinder. When does it extend and when does it retract? This shows you right here is what's required. This between here is actually in motion. And then when it hits here, this is going to trigger 1V2. Then this is showing you what else does it affect. Well, if we drop down here, now this guy right here is off all this time, right? You see that? So this is also going to cause this guy right here to extend. Are we okay? So when this goes true, then what's going to happen? Let me get this right. So we start off, this is retracted. So this is the start right here. This is step 1. These are the position of all these sensors. So this is retracted. The gripper 2A is on off. The pickup cylinder is retracted, and this right here is retracted. So if 1B1 is true, this is going to cause this guy to do what? Extend, right? Okay. Everybody okay? And then if it's extended, it's going to cause this guy right here to do what? Extend. Then that's going to trigger what? 3B2, which is going to cause the vacuum to do what? Turn on. Everybody okay? Then, if this is true, this is going to cause, if the vacuum is on, right, this is going to cause this to retract. That means it's picked up apart. And then we'll follow this on down, which is if 1B1 is true, it's going to cause this guy right here to retract. Now this is when it's in motion. This is what causes it to happen. So this is actually the transition. What causes it to transition? And then this right here is actually the step. So that would be like it says, this retracts. So where we at? So now we're at step 6. So if 3B1 is true, it's going to cause what to happen? It's going to cause this transverse cylinder. I don't know what just happened there. What happened to? Oh, here we go. It's going to cause this right here to extend, which is going to trigger 4B2, which is going to cause this guy right here to extend, which is going to trigger 3B2, which is going to cause the vacuum power to turn off because it's dropped a block, and then it's going to do what? Then we're on step 9. It's going to cause this guy right here to retract. Then we move to step 10. This is going to trigger 3B1, which is going to cause this guy right here to retract, and then it goes back where? Starts the whole thing over. So this is called a step chart. So this actually shows us when the cylinder. So it's kind of like the other one, but it don't tell you the steps. The actual steps are over here. Whether it's extended, whether it's retraction, traction. This is vacuum on. This is vacuum off. This is the pickup cylinder, extending, retracting. This is the traverse. This is causing that thing across the top to move back and forth. So these are what we call displacement diagrams. Some people like this better. Some people like the other one better. And it would be something, you're going to develop both of them. Are we okay? Okay, any questions on that? So these are steps. And then, of course, these are actions, which they're calling displacement. So something is going to happen on these lines right here. Between those lines is actually when it's happening, right? So I'm just going to go to a different color. So this is when it's happening. This is when it decides the actual line, vertical lines is what's required to make it do the next step. So the movement is the actual slanted line. So what they're doing is going through each step. So what he's calling, he or she's calling, this is what they're calling standby, which it doesn't do, it's going to stay in its position. So it'll stay in its extended position between step 1 and step 9. Step 9 is when it actually changes. And that's what they're showing us here, vertical line. And then what this means, this is a signal line. So this means where you look for to see what triggers the next step. And then this shows you the actual sensor that causes this to happen. Are we okay? You need to ask the question because I think there's one on this step. I think there's a function chart and there's a sequence of displacement. Now remember, this is not decision here. That's when it's already the decision has been made, right? So if you say, when does the pickup cylinder extend? You're not going to say, when does it extend? It starts the extension right there, right? Or what's required to cause it to extend. And like I said, it depends on which one you like, on which one you prefer. But you'll get a chance of making both of them. So we'll start off doing the function chart, and then once we do that, we'll try to do the step chart. And like I said, you'll draw it up on your whiteboard that you will be assigned. We got 2 more back here, by the way. We'll leave the, and we got 1 across on the hall there, so we got plenty. So how do y'all want to split the class? 1, 2, 3, 4. We got